All right, guys, here we go. Let's rock and roll here. Thanks, Paige. All right, so we are going to be spending the next, I don't know, we're going to be spending the next month, I would say, on momentum, conservation of momentum. We are going to be starting a big project either Friday or Tuesday of next week, depending on when the materials come in, all based on momentum. So before I get started here, can someone give me a brief explanation of what they think momentum is, what kind of factors influence momentum? Markel. Something that makes you go. All right. So besides something that makes you go, what else does it do besides making you go? Keeps you going. All right. That's how you guys know momentum for the most part is something that is already going will continue to go. All right. Does anyone know the two? It is kind of like Newton's first law. It fits beautifully in with Newton's laws. Does anyone know the two variables that influenced momentum of an object? Velocity is totally one, and what else? Mass. Very good. All right. Perfect. You guys are going to see I did this presentation up. Yeah, just wait. All right. So, what's momentum? Well, I'll tell you what momentum is, boys and girls. Mathematically speaking, momentum is mass times velocity. So any object with mass that has a velocity or a speed is considered to have momentum. All right? Now, you are going to see what the actual written out math formula is, and I bet I already know what your question is going to be. What's your question going to be? Yeah, I don't know why, but momentum is shown with a lowercase p. So when you see the formula on your formula banks that you get, you need to understand that p is momentum. So p equals mv is momentum equals mass times velocity. Okay? So what I have up here, I have a truck and I have a roller skate. I know they look the same size. However, we know that a truck is bigger than a roller skate. So my question is this. Is it possible for a truck and a roller skate to have the same momentum? Think about the variables that make momentum up, mass and velocity. So which one has a bigger mass? The truck has a bigger mass, obviously, right? So therefore, if a truck has a much larger mass, will it be possible for something with a huge mass to have the same momentum as something with a small mass? Julia says yes. I'm going to agree with Julia that yes, it is possible for a huge truck and a small roller skate to have the same momentum. How is it possible for that to occur? If they have the same speed, though, that wouldn't work. Because if one has a large m and the other has a small m and they have the same v, different momentums. Okay, if they have different speeds, which one has to have a higher speed? The roller skate has to have a higher speed. All right? So what we're seeing here is truck has a super high mass, roller skate has a super low mass. However, we can still get them to have the same momentum if we increase the roller skate's velocity so much that it is many times as great compared to this as this mass is to this. Now, I'll explain what I mean by that in a second here. So a really slow-moving truck and an extremely fast-moving skate can have the same momentum. And I'll show you the math in a second. So ultimately, I think momentum is really applicable to football a lot of the time. Because you could think of, I can ask the question of who would you rather get tackled by? Would you rather get tackled by a lineman, or would you rather get tackled by a cornerback or a wide receiver? Well, it depends. The answer is it depends. All right? Because a lineman can have the same momentum as a cornerback or a wide receiver, who are a lot smaller, have a smaller mass. Because what the deciding factor would be then is, well, the velocity at which they hit you with. All right? So a cornerback or someone small in the football field can have as big as or greater momentum than one of the big slow guys in the field. All right? Did you guys see that? Did you like that? Yeah? Ready? Ready? All right, so here's the question that I'd asked before, so I'm going to break it down for you. Under what circumstances would the roller skate and the truck have the same momentum? Well, the roller skate and the truck can have the same momentum if the speed of the skate is much greater than the speed of the truck. And then I asked the question, well, how much greater? So it has to be, this is the key here, as many times greater as the truck's mass to the skate's mass. So my example is, if we have a 1,000 kilogram truck moving at 0.01 meters per second, that will have the same momentum as a 1 kilogram skate moving at 10 meters per second. So 1,000 times 0.01 is equal to 1 times 10, which is both equal to 10. So therefore, if we talk about, it's going to have 10 kilograms meters per second momentum. That is the unit of measurement for momentum. It's not hard to understand, guys. We know the formula is mass times velocity. So take the mass of the object and combine it with the velocity unit of the object. All right, so kilogram meters per second is going to be the unit of measurement for momentum. So does that make sense to you guys? Two totally different objects with different masses can still have the same momentum? Because they're going to have to, only if they have different velocities, and those velocities are equivalent to the differences in their masses. I feel your pain. My dad, growing up, my dad used to call me Roundhead. Yeah, I feel your pain. You know, I'm recording right now, right?
Wait, you couldn't hear that? Did you hear what I said?
Oh, I heard what you just said.
What did you say?
Probably.
Oh, great. No.
All right, I'm moving on here. I'll go back if you need it later. Man, that just disappears. The recording slows down all of my awesome animations. What? That hurts. Hurts my feelings. All right. So before I get into this slide more, I'm going to turn the lights back on, and I wrote a bunch of stuff on the chalkboard that I want to talk about, because I know it's going to be empty words as I talk about it because we haven't applied it to anything yet. But here's the deal. You see these two terms up here. You see the term impulse and you see the term momentum. All right? Before I get into any detail about them, I want you to understand what I have written up here. So what I have written up here, I kind of break down the math equation that you're going to use. So an impulse, I'm telling you right now that the definition of an impulse in physics is simply a change in momentum. So however how much the object's momentum changes, that is described as an impulse. All right? Now, mathematically speaking, an impulse is found by multiplying the force times the time that the objects are in contact with each other, so the impact time. So an impulse is force of the impact times the time of the impact. All right? Now, change in momentum, mathematically speaking, is shown as m delta v. What does delta mean in science and math? Change in. All right? So therefore, we know that a change in velocity can be written as vf minus vi, final velocity minus initial velocity. So therefore, mathematically speaking, change in momentum equals mass times final velocity minus initial velocity. All right? Now we can combine the math formulas, because if an impulse is equal to a change in momentum, therefore, force times time is equal to m delta v, or m times the quantity vf minus vi. All right? I know that's empty words right now. You will see how this is applicable in a couple minutes. So you should, if you haven't, you should write this down. You can do it now or do it later, but I'll turn the lights back on in a little bit. That will be up there for the rest of the class. So you will have time for the math practice. All right, so it says here, if momentum changes, it's because mass or velocity change. But think about this. Think logically about this, guys. If we're dealing with a momentum change, so if we have a car that changes its momentum, I'm using that as an example. What's the more likely scenario, that the car loses mass or that the car loses velocity? Yeah, all right, so that's why I made an m delta v, because it's generally speaking a change in velocity, all right? And we also know that a change in velocity is the definition of acceleration. So you're seeing how all of these laws that we just studied of Newton's laws are applicable to momentum, all right? So if we know the velocity change, that's acceleration, and mass times acceleration is a force. So you can see how we then get the math formula for an impulse. So applying a force over a time interval to an object changes its momentum, all right? Let's look at this statement here. Applying a force over a time interval to an object changes the momentum. I'm going to use a very tangible and real-life example here that you guys, if you haven't seen, you will see coming up in February. What starts in February? Anybody know? Dun, 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 dun. What? Olympics. Yeah. Did you? I didn't hear you. I just wanted to sing. I wanted an excuse to sing. So, in Sochi, you got it. So think about bobsledding. Think about bobsledding. All right? This here, applying a force over a time interval of an object changes the momentum. Does anyone know that the two different, are they positions? Two different types of bobsledders? What's the one person in the front doing in the bobsled? Steering. They're the drivers of the sled. What are the big, strong guys doing in the back of the bobsled? They're pushers. All right? So now, think about this. Think about bobsled in terms of momentum change. When bobsledders are at the top of the track, do they just go, ready, 1, 2, 3, and push and let it go? No. They run with it. All right? So they have a handle of that bobsled, and they run and run and run and run until the line where they have to jump in, and then they get in the sled. All right? They are applying a force for a long time interval. All right? So that means that they are changing the momentum as much as possible to that bobsled. Okay? And again, what you're seeing here is what I have up on the board. I just kind of break it down a little bit more for you on the chalkboard. All right, an object at rest has no momentum. Why does an object at rest have no momentum? It's resting. It's got no velocity. So it says to increase momentum, apply the greatest force for as long as possible. And you guys can think of a ton of examples that this applies for. So what are some examples that you can think of right now? I'm going to give you 3 seconds to think. What's a good example of changing momentum as much as possible by applying a force to something for as long as possible? Say that again? Drag racing, can you explain that? Okay. Sure. So drag racing. Or you can even say driving a car. All right? If you are going to increase the speed of that car, change its momentum as much as possible, you are going to continually push down on the gas pedal. All right? You are going to apply that force for as long as possible. Good example. Any other examples of how you can increase your momentum? Hitting a golf ball. Yeah. If you hit a golf ball or you hit a baseball or hit a softball or wiffle ball, when you hit, guys, you don't just stop when you hit the ball. You follow through. So you are applying a force for as long as possible. All right? Scooter lab. Exactly. Scooter lab. When you were increasing that person's speed, again, you didn't just push and let them go. All right? If you were increasing it, you continually pushed them and applied that force for as long as possible to change the momentum as much as possible. Do we have any bow hunters in here? So, or anyone that's ever shot a slingshot or a bow and arrow, you don't just pull it back a little tiny bit and have that arrow move. You pull it back all the way. And that is because when you let that arrow go, that bow is going to apply a force for as long as possible to that arrow to change its momentum as much as possible. All right? Yeah. The good one. That's really good. That's really good. This one's a good one too. A long cannon versus a short cannon, or a pistol versus a rifle. All right? A rifle, you increase the momentum, or you have a higher impulse. Remember, change in momentum equals impulse. So I can use those terms interchangeably. A rifle has a greater impulse than a pistol does. Reason being is because that bullet is in that chamber the barrel for longer. So the force is acting on that bullet for longer, all right, in a rifle. That's why it has a greater impulse, all right? So any questions of how to increase momentum, what you need to do? And again, it's you guys have done stuff like this in your everyday lives without even thinking about the physics behind it. All right, I think you already have the vocabulary stuff filled in. The first two are definitely more important than the last one. So an impulse, we know that it's force times time, so it's the impact force times the time. Impact is the force acting on an object, usually when it hits something. And the impact force is, well, the force of the two objects hitting each other. All right? All right. This is my pride. This is my pride and joy right here. So here's what we have. So we talked about increasing momentum on the previous slides. Now I want to take a little bit and talk about decreasing momentum. So what we have here, we have two cars, mass and velocity. So what do you get when you multiply mass and velocity? Momentum. So what I'm trying to get at here is they have the same mass shown by the same size m and same velocity shown by the same size v. So we have two cars with the same momentum, all right? When I tap on the board, they're going to go. They're going to move. One is going to hit a hay bale. The other is going to hit a brick wall. Ultimately, think about this. What is the outcome going to be? What's going to happen when both of these cars hit those objects? Well, they're both eventually going to stop, right? Okay. Which one's going to stop first? The blue one. Good. This one's going to take a little bit while to stop, a little bit longer to stop. However, please understand that because they have the same momentum, all right, and the end result is the same, which is going to be they're going to come to a stop, their change in momentum or their impulse is exactly the same. But think about, that does not mean that the outcome of what's going to happen to the cars is the same. Which one's going to have more damage? The blue car or the gold car? Blue car. And here's why. Because what you're going to see that I'm going to talk about a little bit more detail next is that the time of impact has a great effect on the force of impact. So when I do this, this one gets crushed, this one just comes to a stop. Their initial momentums were the same, their final momentums were the same, meaning their impulse or change of momentum was the same. However, question is, why are the outcomes different? Well, because of this. You're going to see that the shorter the time of impact, the greater the force exerted on that object. That's why I have a small t and a big F here. A small time of impact equals a large force of impact. Up here, I have a large time of impact, which is shown by a small force of impact. So if you want to decrease the force of impact, you want to extend the time of impact. All right? So, and I can say vice versa on that too. If you want to increase the force of impact, you want to decrease the time of impact. All right? Remember when we were talking about Newton's third law, and the example we used was people punching walls? And people say, well, what if you punch through a wall? Well, if you punch through a wall, all right, if you punch through a wall, your time of impact is greater because it's a longer impact with the wall, meaning that your force is smaller. All right, comparatively to punching a brick wall that stays where it is, where the time of impact is super small because it's a hit and stop, meaning the force is really big. All right? This information here is going to be super, super important when doing our project. We are doing a big project coming up, like I said. Here is what your project is going to entail. I know someone's going to say, we did this in middle school. You may have, but you had no idea why you actually did it in middle school, nor I guarantee you couldn't explain the physics behind it. You are going to be creating an egg drop container using only popsicle sticks, balsa wood, and hot glue. We're going to be dropping those containers with a raw egg in it off of the steps out here. Like I said, you have to use this bit of information in order to make that egg not break. So think about what this says here. It says, the longer the impact time, all right, the smaller the acceleration or deceleration. So whenever it's desired to decrease the force of impact, extend the time of impact. This here is the key to understanding decreasing forces of impact, all right? And this applies to all of you guys, being 16, 17, 18 years old, because you're relatively new drivers, all right? Well, that's relatively new. How can driving a car or car accidents apply to this? What kind of safety features do cars have? Specifically, yeah, exactly, airbags. So think about this. You're driving in a car. You're driving this car. You have a passenger in the passenger seat. Both of you have the same mass. So therefore, if you're going the same velocity and you have the same mass and you both get in a car accident, yeah, you're both going to have the same impulse. Same change of momentum. You're both going to come to a stop. However, the driver's seat, when you get in a car, they're going to have an airbag that comes out. So therefore, the time of impact on the driver, is it larger or is it smaller than the passenger? It's smaller, the time of impact? The time of impact is going to be larger with the airbag, meaning that the force of impact on that driver is smaller compared to the passenger who will maybe hit the dashboard or the windshield if they're not wearing their seatbelt, where the time of impact is super small, which means hit and stop, the force is going to be a lot larger on them. Okay? There are tons and tons and tons of examples that you guys experience every single day dealing with decreasing momentum and decreasing the force being exerted on the object. And I'll talk some more about these examples. So if the time of impact is increased by 100 times, then the force of impact is reduced by 100 times. What type of mathematical relationship is this when one goes up and the other goes down? Inverse. Yeah. So therefore, as far as force and time go, if the time of impact goes up, the force of impact goes down. If you need to write inverse here, please do it. So this is an inverse relationship. Okay? So can anyone think of just some examples before I give my examples of increasing the time of impact will decrease the force of impact? Think of some examples. Or you're on the right track. So Tony said you slow down, slow down, slow down, and then hit bumpers. What you could say is you kind of hit them and then you slow down instead of just coming to a jarring stop. That would be more applicable. All right? Because remember, it's got to be the time of impact. What else? What can other examples be where if you increase the time of impact, you decrease the force of impact? Sure. Yeah, totally. So, yeah, what Cody said is instead of swinging, you bunt. All right? The impact time is going to be a lot smaller. Well, I guess there's going to be more to it than just that. But let's think about baseball. Let's go with that. Let's go with football again. All right? You play football, right? Were you a wide receiver? Perfect. Perfect example here. So, when you were taught to catch a football, how were you taught to catch a football as a wide receiver? With your hands. Yeah. Exactly. All right? So football players are taught to catch the ball with their hands and not with their bodies. The reason being is exactly because of this. When you catch a ball with your hands, you go with the ball. So when you go with that ball, you are increasing that time of impact, which decreases the force of impact. Compared to catching the ball with your chest or with your body, the time of impact is super, super short. Ooh, that was a good clap right on my microphone. I bet that's going to sound good when we play it again. Meaning that the force of impact is going to be very, very high. All right? Or if you watch a baseball game and you see a screaming line drive go into the crowd, and you see the person that catches it, they go, whew, they go like that. Same example. They're increasing the time of impact with that ball, meaning that the force of impact on their hands is going to be a lot smaller. Same thing. All right? I'm going to ask for one more example. Can anyone think of one more example of how this is, where you see this or how you've experienced it? A goalie. Sure, same deal. Yeah, goalies will go with it. Instead of having their hands out like this, all right, they're going to bend their arms when they catch it. Perfect. So here's a bunch that I came up with. So padded dashboards on cars. Yeah, all right, that's going to be much better for your face hitting a padded dashboard than it is if the dashboard were just straight up plastic or metal, all right? Because you're increasing that time of impact, decreasing the force. Airbags, we talked about it. Safety nets in circuses. So the high wire act. That crazy person's up there walking and they decide that if they fall, well, they hit that safety net and the safety net increases the impact time, which decreases the force compared to splatting on the hard ground, all right? We talked about that. What else? A boxer getting punched in the face. Boxers don't lean into a punch, guys. If they do, they're not very good boxers. Boxers, when they get punched, they'll go with it. Same reason. They're increasing the time of impact, which means they're decreasing the force of impact. Flexing your knees when you jump. When you land, you don't keep your knees straight like this, because that means the force on your legs is much greater than if you bend your knees with it. All right? Wrestling, you wrestle on mats instead of hardwood floors. Dropping a glass onto a carpet instead of the sidewalk. All same things. Where, remember, we could take any of these examples in the change of momentum of these objects. So if we're talking about dropping a glass dish onto a carpet instead of a sidewalk, their impulses are the same. Their change of momentums are the same. Because as they're falling, they have the same momentum, and they're both going to come to a stop, but their outcomes are different because of the time of impact and how that affects the force of impact. Does that make sense to you guys? All right, I know I'm doing a lot of talking today. I'm getting towards the end here. Here we go. Bruiser Bruno. So in that case, he went with the punch, meaning the time of impact was greater, force was smaller. Whereas this Bruno is going to go into it, meaning very small time of impact, which is greater force of impact. Bungee jumping. I'm going to show you guys. I'm going to show you two videos of bungee jumping. All right. One is a rather archaic form of bungee jumping, and the other one is today is much safer form of bungee jumping. So I'm going to show you the first old type of bungee jumping, which has been happening for a while here. So you are going to see some tribal nudity. Sure, sure. Hold on one second. I'm going to need to stop my recording here.